Bridging the gap between chaotic continuous fields and strict integer sets is the core tension in physics. Unbounded potential must collapse into geometric order. Standard Zermelo-Fraenkel set theory relies on arbitrary starting points to explain this order. The theory of infinity establishes a different ontological map. It dictates that the mathematical cosmos is extracted entirely from an indeterminate absolute totality. Moving from an unknowable void to a structured universe requires a primal dichotomy. This transition is driven by a single formative operator, symmetry. This symmetrical interaction enforces the rules of the golden set. The golden set is a strict, bounded environment where mathematical invariants are forced to achieve absolute closure. The universe does not materialize randomly from nothing. It operates as a meticulously governed spatial boundary, filtering continuous potential directly into discrete, knowable reality. This framework culminates in the master theorem of continuous-discrete topology. The theorem proves that macroscopic thermodynamic systems, fractional derivatives, and complex variables are all governed by one singular mathematical law. Traditionally, applying continuous calculus to extreme limits is assumed to generate chaotic or infinite outputs. Inside the golden set, this continuous math generates measurable geometric friction. Instead of fracturing, the continuous functions organically annihilate into exact, mass-conserved, closed-form equations. The exact physical and topological constants we observe in reality are forged directly by the mathematical tension generated at these continuous discrete boundaries. The fifth foundational pillar of this mathematical law is the Vieta Annihilation Theorem. This diagram maps the evaluation of the manifest phi derivative. The manifest phi derivative is a specific finite cubic polynomial generated exactly at the 10th rung of the continuous discrete boundary. To decompile this, we extract the first Vieta parameter, the algebraic sum of the roots. The derivation yields an exact topological expression matching an empirical baseline capture of negative 0.744136. We then extract the second Vieta parameter, the product of the roots. This derivation identically aligns with the empirical capture of 0.23004. Feeding these two parameters into a ratio operator, dividing the absolute sum by twice the product, forces the continuous variables into a tight topological bottleneck. Inside this bottleneck, a gamma annihilation occurs. The underlying topological mass, represented here by the square root of 5, perfectly cancels itself out. Shedding this mathematical mass collapses the entire system into a pure Fibonacci integer scale, leaving exactly 21/55. Advancing this discrete fractional mechanic to its absolute continuous limit reveals the final continuous target. It perfectly converges on the golden ratio. This mathematical sieve physically sheds geometric friction. It demonstrates that holistic topological mass is exactly conserved when it returns to the golden ratio. Beyond algebraic integers, this boundary condition strictly governs the physical geometry of the complex plane. Applying continuous fractional derivatives to discrete polynomial lattices forces their roots to collapse inward, generating heavily compressed spatial coordinates. This unrolling mechanism takes the single one-dimensional real root of the discrete Fibonacci sequence and locks it in as a baseline radius. The paired complex roots then project that exact geometric radius into the imaginary phase, tracing a perfect quarter circle arc. This geometric projection establishes a topological mirage. A topological mirage is a permanent structural signature that perpetually hovers a microscopic distance from pure continuity to ensure mass conservation. Complex numbers are real, rotational energy states. They serve as the physical thermodynamic exhaust that a mathematical system expels to conserve its internal spatial volume. Elevating this framework from two-dimensional Fibonacci topology into three-dimensional Tribonacci geometry reveals precise mathematical symmetries. Tribonacci geometry is the three-dimensional extension of the Fibonacci sequence, where each integer is the sum of the three preceding it. This table maps out what happens when you shift the constant term of the structural derivative across adjacent integers. Doing so establishes the Pauli Tribonacci equilibrium. Applying a standard differential calculus drop to these fourth-degree characteristic polynomials isolates their continuous limit rails. Executing this exact differential drop at rung 9 of the three-dimensional Tribonacci space unrolls the geometry into specific defined integer values. Processing these distinct 3D variables through Vieta's formulas extracts the holistic mass of the system by isolating the product of the roots. The discrete integer state of this derivative yields a precise finite fraction, 137/88. The prime numerator that emerges here, 137, is Wolfgang Pauli's fine structure constant. The fine structure constant is the physical number governing all electromagnetic interactions in the universe. As this sequence extends to infinity, the continuous limit of this physical rail perfectly tracks the alpha-cubed tensor. Pure abstract differential operations applied to discrete three-dimensional sequences naturally and inevitably build the numerical topography of quantum physics. If geometry dictates physical constants, can pure probabilistic noise bypass this structural determinism? We analyze this by applying stochastic thermodynamics, running continuous statistical limits against discrete mathematical sets, using Monte Carlo random variables. When a randomized sequence is trapped inside the boundaries of a localized golden set, the system operates as an ergodic sieve. An ergodic sieve acts as a physical funnel that forces chaotic inputs to conform to a dominant macroscopic state over time. By upgrading this filter to evaluate the squares of these random variables, the mathematical upper boundaries violently expand. This massive exponential scaling actively crushes the internal chaotic noise of the smaller probabilistic numbers. Statistical randomness is bound by geometry. The mechanics of probability are permanently slaved to the physical, topological mass of the discrete boundaries containing them. The final boundary test involves macroscopic scaling via the dyadic octave lift. The dyadic octave lift is an operator that elevates mathematical exponents through extreme powers of 2. At low degrees, polynomial manifolds generate graceful, sweeping curves. As these equations are pushed to the 32nd and 64th degrees, the topological mass undergoes immense compression. At extreme dimensional limits, all continuous curvature is annihilated. The manifold violently crystallizes into a rigid, straight-edged Euclidean unit box. The 8 exact coordinate points where this box slightly bulges outward represent fractional scars. Fractional scars are the unyielding physical friction of discrete integers, refusing to allow a flawless infinite square. This friction is present at every level of the mathematical cosmos. We observe it from Vieta's algebraic right annihilation to the geometric unrolling of the complex plane, down to the final Euclidean confinement of the hypersquare. The physical constants of reality are forged by the immense, unyielding friction between infinite continuous fields and the absolute boundaries of discrete geometry.